Warning: sodium chlorate and perchlorate are oxidizers and may explode on contact with reducing agents or acids. Fire safety protocols must be in place. Hi guys, this is MIH. First of all, Happy Chinese New Year to every Chinese citizen and every countryman residing abroad. This year's Spring Festival was much more exciting than the past years because the government allowed firecrackers and fireworks in many rural areas and even cities. The only bad bit was that the fireworks were incredibly expensive and not as spectacular as I expected. Today I'm going to make one of the prerequisite materials for pyrotechnics, sodium perchlorate, via the thermal disproportionation route. We start by weighing 50 grams of ethanol in an alcohol stove made from 2 soda cans. I strongly recommend another heat source such as an electric furnace because the stove consumes ethanol especially fast. I made 41 grams of sodium chlorate in my last chlorate batch, and I'm going to convert all of them to sodium perchlorate in 2 batches. I first added around half of the sodium chlorate in a porcelain dish. Try to avoid metal containers here. Some ethanol was poured on the base of the iron stand and ignited. The burning ethanol heats the ethanol inside the stove and ignites its vapors. After the ethanol on the outside burned out, the flame becomes self-sustaining, and I adjusted the position of the dish. Soon, the sodium chlorate starts melting and releases some bubbles. It is largely water vapor with traces of oxygen. Sodium chlorate is very hygroscopic and likes to absorb water, so be sure to heat it evenly and avoid volume bubbling. When the bubbles disappear, everything should be completely molten and no more water should remain. As I continue to heat the sodium chlorate, it starts releasing bubbles again, but this time oxygen instead of water vapor. Some sodium chlorate decomposes into oxygen and sodium chloride, but the majority of it disproportionate into sodium chloride and sodium perchlorate. The melt is heated at this temperature until all the ethanol burns out, which took around 30 minutes. 40 minutes later, the mixture cooled down and solidified. You can see that its surface is not flat, but swells up unevenly. This is a good sign that shows a complete reaction. The mixture also shrinks as it cools, so it didn't stick to the porcelain dish and was relatively easy to remove into a beaker. I then smashed it with a spatula, and you can see the porous structure inside the cake, indicating that large amounts of gas have been released. The cake was quite easy to crush with a mortar and pestle, and it weighs 15.3 grams, which means we lost a few grams of mass as oxygen and water vapor. Now we have sodium perchlorate, but it is mixed with sodium chloride and unreacted sodium chlorate that I need to separate. To do this, we can exploit the good solubility of sodium perchlorate in organic solvents such as acetone and ethanol. This is also why I didn't start the experiment with potassium chlorate, as potassium perchlorate is poorly soluble in organic solvents. I added 30 milliliters of ethanol in the 15 grams of powder and boiled it on a hot plate for 10 minutes. I then vacuum filtered the mixture while it is still hot to separate the sodium perchlorate from the other salts. I boiled off all the ethanol on a hot plate and ended up with some fluffy white solid. I crushed it in a mortar and transferred it into a vial. In the end, we have 5.21 grams of sodium perchlorate. The yield wasn't ideal at all, but that was to be expected with my crude procedures. I then processed the other half of sodium chlorate in nearly the same way. However, there are apparently more sodium chlorate in the second half, so the regular heating time of 30 minutes isn't enough anymore. As you can see, I got a solid cake due to incomplete reaction instead of a porous mixture like last time. In the end, I only got 5.91 grams of slightly yellow sodium perchlorate. I didn't retain this product because its yellow color shows that it is contaminated with organic materials, which is especially dangerous in pyrotechnics. Instead, I combined it with the 2 batches of filtration residue, extracted them with ethanol again, and got another batch with a higher quality. This is the final sodium perchlorate product from all the extractions, and it weighs 9.65 grams, which represents a yield of 29%. If I completely react and harvest the second batch, then I can probably get 50 to 60% yield, which is typical for this method. Future improvements include using electric heating instead of the alcohol stove and a saucelet extractor for the extraction step, although I would prefer the less laborious electrolysis route. Anyways, I still need to test my product to see if it contains large amounts of chlorates, which may accidentally blow things up. I scooped 4 samples roughly equal in amount. The 2 on the top are marked perchlorate, and the 2 on the bottom are the residue left after their extractions. I first added a few drops of hydrochloric acid on 2 of the samples, and you can see the residue has a much more significant yellow color, indicating the presence of chlorates. To the other 2 samples, I added concentrated sulfuric acid, and both samples turned yellow, but the residue has a much stronger reaction than my product. The tests shows that my sodium perchlorate is pure enough to be used in normal pyrotechnic applications. Thanks for watching.